Good morning, everyone. Today I'm going to be giving a brief update on the use of technology on TfL. The use of technology on TfL is very much something we do in partnership with our suppliers, co-partners, because we find through collaboration that's where we get the best results. And therefore, what you see today is some of the partnership work that we've been doing with people in industry. First and foremost, on TfL, the tube is probably the thing that gives us our greatest challenge. As you can see from the slide and the photograph, space is constrained. It's difficult to access. Times of access are limited. And if you like, there's nowhere that we can store things going down. So consequently, a lot of what we do with technology is driven by logistics, and more logistics as we go through for these things. One of the first things I'd like to talk about is the track adhesion management project that we're running in conjunction with RSSB. Over the last few years, London Underground has built up, through bitter experience, quite an understanding of the problems of leaf fall. As an operator, London Underground has no desire to have autumn timetables. Therefore, tools have been developed in-house. We're currently in the process of working with RSSB on a system that should work to predict what the impact of leaf fall will be, and therefore we can avoid safety issues as well as losing availability of rolling stock through wheel flats. So as part of the system, developed something called PAMS, or the Predictive Adhesion Management System. The software indicates the likelihood of low rail adhesion based on a station-to-station run, as you can see in the shot that's on the screen. The logic engine for PAMS is fed by inputs from the Met Office in terms of sort of wind and rainfall, together with likely leaf fall forecast, as well as the input from the maintenance teams in terms of what state the vegetation is, the type of vegetation, the topography through which the tracks run, as well as rolling stock operating characteristics. It's very much been something that's an in-house development using agile software, which I'll comment on shortly. But so far, the leaf fall season at the back end of 2019 was probably the best we've had for a couple of years. And what we're finding from calibration work going on at the moment is that the PAM system is coming up comparable to what we would have expected with the in-house ACAT tool that we've been using for the last 15 years. Moving on to Sherlock point machine performance. Part and parcel of, again, on the underground is, if we have a failure, how long it takes the TOs to get to site to fix the failure. So consequently, we've developed some real-time monitoring systems. This particular example is for the Sherlock point machine. The system measures the power that's taken to driven the switch rails. If it's operating normally, we know what that power should look like. Therefore, if we start to need greater power, then it suggests that something goes wrong and that we need to intervene. The system measures the power, and then text alerts are sent from the particular receiver to the TO first to notify them there's a fault so they can start to get to site, but it's then followed up with a series of emails giving detail of what the particular issue is, so that it means that when they arrive on site they have a good handle of what the problem could be, and therefore it will reduce the time to fix on site, and therefore the service is up and running sooner. And you can see on the right hand side here is an example of the sort of performance plot you've got of power against movement of the switch going through. System, as I say, each site is independent and processes its own data in real time. This means we've taken out single point failures. The system has plenty of capacity for the future because, like all systems we've got so far, but we want to improve our predictions, improve the way that we process data. It doesn't rely on people to view and analyse the data, so it means they've got more time available to deal with other bits and pieces going on. Plus, it means when they get to site, they've got greater confidence in what it is that needs to be fixed. And again, it's a system that's modular. We can drop in as and when we go about installation of the Sherlock point machine. Next particular one I want to pick up on, again, it comes around this issue of line-side storage. So we've developed a lightweight trolley that we can take apart into different parts that can easily be handled up and down escalators. I realise from people from Network Rail that may seem quite an odd thing to say, but from the viewpoint of London Underground, it's amazing how much we use escalators for different bits and pieces. And therefore it's quite critical for that. One of the other things we've also done as well is something I touched on in the winter seminar about the use of lithium batteries. We've also reconfigured battery technology such that once upon a time we would have used 8 lead acid batteries, each weighing 25 kilos. Obviously, if you've got 8 of those, you've got to take down an escalator. That's quite a bit of work involved with doing that. We've now tapped into the lithium battery technology such that we've replaced those 8 with 4 batteries. The 4 batteries weigh something like 13 kilos each. So in itself, we've saved on a number of trips up and down the escalators, plus 75% reduction in handling. The batteries come with their own monitoring system, so we can see how much power is in there, how much power is being used on a shift, and therefore we don't have to constantly keep worrying about how we're going to charge the batteries. We charge the batteries when they need to be charged, and therefore we get a longer life out of that particular asset. Something else that we've been doing is looking at the use of rail dampers to suppress rolling contact noise and corrugation growth. Effectively, if you can imagine, it's a block attached to the web of the rail. The interesting thing about these are that they've actually got 14 smaller masses within the casing, each of which is free to move in both the X and Y direction, and therefore has the ability to dampen more effectively. This system has already been widely used in Hong Kong, and we've been carrying out trials on the underground. This particular one is a photograph taken from the Northern Line between Kentish Town and Camden. Has it worked? Well, if you can see from the graphs that you've got there, certainly in terms of damping, there is a performance improvement there of the range of about 5 dBA, which is quite significant. In Hong Kong, they've been able to tune the system and achieve savings of up to 10 dBA in terms of rail noise, which is actually quite considerable. So what we're now looking to do is to extend this trial onwards to have different sections to understand how it can be used in the LU tunnel environment. TfL, like Network Rail, is using drones to undertake surveys. On a railway that is already resource constrained, there are some parts worse than others. Drones allow us to access areas in a far shorter time, make best use of the time that is available to us, so therefore we're then able to collect the data that we require both to understand our assets and to undertake track renewal work. As you can see from the slide that you've got here, On the left-hand side is a traditional CAD image. On the right-hand side, you can see the quality of the data and the information that the engineers can see from what was recorded by the drone surveys. And that gives us a better understanding of what's going on site. Because again, one of our issues are that for a number of these sites, we can only get to them in engineering hours. During daylight, the visibility is not as good as we would like, and therefore you can miss things, whereas through the drone surveys, we have good imagery. What we've also done in conjunction with the surveyors is taken also photo techniques, which again, nothing new in the industry, but it's technology that there's available to us, and put the two together so that when our engineers are doing work in response to, say, questions from the operator where a train has been gapped, or undertaking track renewals, that they can very easily see what's going on site without having to put boots on the ground. The next area we've been doing work on is in regards with surveys and with cloud surveys, with the IMU data collection, which, if I don't get this wrong, Alison will throttle me. We use a system from Amberg called the inertial measurement system. This measures track curvature, cant gauge and gradient, both absolute and relative. It uses gyros to measure the changes in direction. We've also hooked this up with scanning technology, which means then that we get a very accurate picture of what's in the ground, and we can then take that forward, for instance here, in terms of assessing impacts. So for this one, as you can see, we have some structures that foul the structure gauge. Normally, or once upon a time, you'd end up sending gangs out to go and fix something in the vicinity of these areas. Using these techniques, we're able to see what it is on the feature that is causing the problem, and therefore saying to ourselves, in terms of before the gangs go out, what is it that we want them to do, which are the particular cabinets we want them to do. So as you can see here from a scan, the red and yellows represent the degree of infringement to the structure gauge. Effectively, it's a heat map, and therefore we can get them to focus on what needs to be done, overall saving effort. As well as using it for that sort of thing, we can use it for design reviews, and equally in terms of the engineers understanding what the problems are. Every engineer on TfL through the internet browser has access to two products from Leica, looking at called TrueView and Jetstream, that enable yourself to put yourself in the 3D space to see what's involved. As part of that, you can make measurements on the screen to understand the distance between structures, where, say, you've got the potential if you need to drop rail strings or cast crossings, what space is available to you to help you plan the particular job, or if there's a particular issue that's causing a problem that's been related by the operators, that you can interrogate the data sets that are there to see if we can identify before sending someone out to site. For TfL, platform train interface is a really big issue. TfL is bound by the RVA regulations, and therefore we have to try and make sure that we manage the gap as best as we possibly can for our travelling public. Part and parcel of that, though, is that if you've got a station that's 150-year-old, when they built it, they didn't have the RVA regs in mind when they built it, and therefore we can end up with a scenario where for half of the platform, as we have at Baker Street Platform 2, it's straight. The other half consists of a transition curve from a 200-metre radius curve. Therefore, you're going to have doors where you've got sizable gaps, as you can see in the photograph in the forefront there, but further as you go through the platform, then the gaps change. What we're looking to do at Baker Street is to see how we can manage it. So the first thing that we've done for a couple of years now, working on the psychology of the travelling public, is to use what they call blue lights to highlight that there is a gap and therefore making people aware. However, we know from observing CCTV that unfortunately when people are on their phones, they don't mind what colour the gap is, they'll still go down there. Something else that we are aware of, that we've been looking at, is the passive gap fillers, as you see on the bottom right there, that allow, if you like, the train to stroke the edge of the platform and therefore provide a gap going through. Probably the thing that most interests us for sorting out Baker Street Platform 2, but we'll be looking, if it's successful, to apply it elsewhere, is the use of active gap fillers. As you can see on the left-hand side, these gap fillers are activated by train arriving in the platform. So there are obviously a number of tests and syncing that need to be done. The decision has been made that it won't be synced directly into the signalling system, but we'll have fail-safes that will tie into the signalling system, such that if it fails to activate or when it should be going in, it doesn't, the train is prevented from leaving the platform. We hope to go live with that trial in the next year, and hopefully in subsequent sessions for these we'll be able to report how it's gone or otherwise. Something else that's sort of been quite close to my own heart has been one of the way that we've gone about doing gauging, and we've taken allowances into case. We like to think from an underground things we work the tolerances quite hard, but we are aware from RSV funded research and working with the likes of David Johnson that there are actually other ways of looking at these things, and that we can look at probabilistic gauging to say, have we got a real issue or not? So for instance, if you take this assessment that D-Gauge ran for us for Baker Street Platform 2, we were able to take a situation whereby the worst case step moved from an 11 mil infringement to being almost 40 millimetres clear, just by looking at the tolerances. So there's definitely something there that we can tap into in the future. One of the other things that we do is obviously we've got quite a lot of direct fix concrete slab track. We've got a lot of concrete track that also needs replacing. As you can gather, getting access to certain lines to do this work is difficult. So therefore, when we do that work, we have to make sure that we do as much as we possibly can to the best possible standard. Working closely with Balfour Beatty, we've looked at the various stages of the process, and getting concrete to site and getting it to cure in the time available to us is a difficult thing, because often we have to pump over 800 metres before we pour the concrete on site. So one of the things that Balfour Beatty came up with, that we've supported them through there, is having what is referred to as converged nodes that measure the strength and temperature of the concrete as it goes off, such that we better understand the concrete that goes in. And also, it then allows us, as we've subsequently found at Camden Town, that actually we can start certain activities sooner based on measuring what the strength of the concrete is. So if you can see this particular photograph here, as you can see, Camden is a particularly complicated site to work, but because of measuring the strength, we can start things sooner. Balfour's also brought in a system of using mesh to separate the pour into stages and therefore get the better quality and able to get in and do the work for it for these things. not only do we want to sort of measure during the weekend, what we can also do is use the data that's available to us to say to ourselves, well, how did things go during the particular weekend? What were we doing at each stages, and therefore what can we fine-tune to improve delivery with the potential of getting more work done on the next time that we get a closure. So that brings me to the end. I was never quite sure which slide to fit on, but having listened to Gareth, I think there's probably a slide after his own heart. But we too are looking at composite materials, and this is an example of a long timber bridge renewal that took place about a month ago, using the Sekisui composite bearers. Thank you.